Okay, today we are looking at graphing polynomial equations. We've kind of been doing a lot of this more or less with our wave. Today we're just going to kind of add in the y-axis. But like I said, some of this should feel fairly familiar. So polynomials are classified by their degree. The graphs of the polynomial functions are classified by the degree of the polynomial. Each graph, based on the degree, has a distinctive shape and characteristics. So again, we've kind of been seeing this when we've been doing the wave. So we know our linear hits the graph, the x-axis one time, it's got 1, 0. It points up to the right, our quadratic, cubic, quartic, and our fifth degree function. And so today we're also going to kind of introduce this idea of end behavior. And again, we kind of did touch on this a little bit with the wave because we talked about like how do we know where to start and all of that stuff. So end behavior is a description of the values of the function as x approaches infinity. So this is how you'll see us write that. So as x goes to infinity or negative infinity, as x approaches negative infinity, the degree and the leading coefficient of the polynomial function determine its end behavior. It's helpful when you're graphing a polynomial function to know about the end behavior of the function. Okay, so we know that when we were using the wave, we talked about, okay, well, if it's positive, right, if that leading coefficient was positive or all the signs on our x were positive, we knew we started in that top right. So as x went to positive infinity, so did our function. It went to positive infinity. And then down here again, we have as x goes to positive infinity, our function goes to positive infinity. That's up to the right. Now, with odd degree functions, we talked about how they should be pointing in the opposite directions. So as x goes to negative infinity, we can see that the function p of x is also going to negative infinity. So as I go left, my graph is pointing down. Now, when we have an even degree function, we said they should end facing the same direction. So whether it's negative infinity, I'm going up, or positive infinity as I go to the right, I'm going up. So that's all when our A is positive. Now, when A is negative, we know it flips. It does that reflection. So that's why we would start below, on our wave. So as x goes to negative infinity, right, so as we're going to the left in an odd function, we know we should be pointing up, going to positive infinity. And as I go to the right to positive infinity, my graph is pointing down to negative infinity. And then again, when it's even, they're both going to negative infinity. So as x goes to negative infinity, as our x goes to the left, the function's going down. As x goes to the right, the function is going down. And so again, we kind of talk about these general rules that we were using with the wave, that if they have a positive leading coefficient, the graph starts up on the right. And if it has a negative leading coefficient, then the graph starts down on the right. And then we talk about that degree. Remember, if it's even, so 2 or 4 or whatever, then both ends point in the same direction. And if it's odd, then they're going in opposite directions. And again, all that should be somewhat familiar because we did use all of these rules with the wave. Okay, so now what we're going to do is basically determine the end behavior based on just the leading coefficient and the degree. So the first thing we're going to do is identify the leading coefficient, degree, and end behavior. So our leading coefficient, well, that's that first number, that's A. So A here is 2. And the degree, remember, that is the first exponent. So our degree here is 5. Okay, so we have a positive leading coefficient and our degree is odd. So we know that these should be starting on the top right, and it will end in opposite directions because it has an odd degree. So as x goes to positive infinity, so as we're on the right side of that wave, we know we're at positive infinity because we'd start above. And then because it's odd, we would be going, as we went to the left, we know that it should be going down. So we should be at negative infinity. All right, here, number 2, our leading coefficient. All right, we see it right there. It's -4. And then our degree is that first exponent, and it's even. It's 2. All right, leading coefficient that's negative. That means that we're starting down on the right side, and because it is an even degree, it means both ends are going to be pointing the same direction. So we know that as x goes to positive infinity, so on the right, we would start below, and it would be, negative infinity. And then because this is ending in the same direction, as we go to negative infinity, our function p of x would also approach negative infinity. All right, our next section is kind of looking at the graph and seeing what we can determine from there. So identify whether the function graph has an odd or even degree and whether there's positive or negative leading coefficient. Okay, pointing in the same direction, that's even. And when it's reflected upside down, we know that that leading coefficient was negative. And you don't have to say the else, you can just say even negative. All right, so we're pointing in the same direction. So again, we know it's even. It's opening up, so we know it is positive. All right, we are ending in opposite directions, so we know our function is an odd degree function. And because we're starting up on the right, we know that it was a positive leading coefficient. Okay, so now what we're going to do is we're going to put all the stuff that we've been working on and doing, we're going to put it all together and graph these polynomials. Okay, so the first thing we're going to do is we're going to find all the roots using rational root theorem or factoring if factoring is available, and you can do it that way. Then we're going to find the y-intercept by plugging in 0 for x. We're going to identify the end behavior of our function, and then we're going to plot the points on the coordinate plane. Okay. So the first thing I need to do is I look and I say, okay, can this factor, it possibly could by grouping, but then when I see, well, no, there's no GCF that would kind of make these numbers end up being the same. So that means I need to use my rational root theorem. So I start with my p. Remember, p are the factors of the constant. So plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Q is that leading coefficient, so it's just plus or minus 1. And then remember, P over Q, we take each one of those. If we're all dividing them by 1, they're not going to change. So I'm just going to draw an arrow because those are going to go down there. All right. Now, I told you whenever we started with rational root theorem, I typically start with 1 or negative 1 and see if one of those is going to work. So I'm going to start with 1 first. So I check and make sure I don't have any holes. So I have x to the third, x squared, x, and a constant. So I can just write my coefficients. So we start with the 1. We bring down our 1. 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. That's negative 2. And 1 times negative 2 is negative 2. Well, that doesn't work. So it's not 1. So let's look at, see if negative 1 works. Well, I'm going to put my 1, my 3, negative 6, negative 8. Bring down my 1. 1 times negative 1 is negative 1. 3 minus 1 is 2. Negative 1 times 2 is negative 2. Combine that to get negative 8. Negative 1 times negative 8 is positive 8. And so there we go. There's one of our zeros. So I'm going to go over here and just kind of start my list. So I have negative 1. Okay, now remember that if this is x to the third, then this has to be x squared. And we think about, okay, well, this is x squared plus 2x minus 8 equals 0. So are there two numbers that multiply to give me negative 8 and combine to give me positive 2? So remember, you can do, if you still need your x method to organize, then do that. Negative 8 and 2, that'll be positive 4 and negative 2. So I have x plus 4 and x minus 2 is equal to 0. So then our other zeros, we can go write them over here, are negative 4 and positive 2. Okay, so number 1, we found all the zeros. Step 2, find the y-intercept by plugging in 0 for x. Well, so if we have it in polynomial form, remember it's really easy. It's always just the constant because that would be 0, 0, 0. So the y-intercept is 0, negative 8. And now let's talk about end behavior. Okay, so we're going to say as x approaches infinity, what does f of x do? Well, it's positive, it's odd. So on the right-hand side, like we're thinking about the wave, as x approaches infinity on the right-hand side, we will be above the line and it will be going to positive infinity. Now, because we are an odd function, when I'm going to negative infinity, I know that my function is going to be going the opposite direction. So it's going to go to negative infinity. All right, so now I technically have 4 points I can plot. I have my zeros and I have my y-intercept. So remember previously when we were doing the wave, we said, well, it doesn't really matter how far up you go. Now we're going to care. We're going to care about it. So we're going to go at -1, -2, -3. We got -4, +2, and then -8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so there's our y-intercept at -8. We have a 0 at 2, a 0 at 1, and a 0 at 4. Now, what's this going to look like? Well, really now we're doing the wave. A was positive, so we're starting above. So we're going to hit that 0. This time we're going to go all the way down to hit the y-intercept, come back up, and then go back down. So this is, again, this makes this just a little bit more of an accurate representation because now we can see the change, how far up or down it goes with our y-intercept. All right, let's look at a next equation. So our next polynomial, we have x to the third minus 2x squared minus 5x plus 6. So again, I can kind of think, does this factor? This is not going to factor, so we're going to use our p and q and p over q. So my p, my q, my p over q. So I have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Q is just plus or minus 1. So my p over q is just my p. So I'm going to, again, I always like to start with 1. So I put my 1 in the little box. I check. I've got x to the third, x squared, x, and a constant. So I don't need any placeholders. So I have 1, -2, -5, and +6. Bring down my 1. 1 times 1 is 1. -2 plus 1 is -1. 1 times -1 is -1. Combines to give me -6. And 1 times -6 is -6. All right, we found our first 0. So I'm going to go, back up here. X is equal to +1. Okay, and again, I want to think, because this is an x to the third, this makes this an x squared. So I have x squared minus x minus 6 is equal to 0. So I'm thinking what multiplies to give me -6 and combines to give me -1. Well, that would be -3 and +2. So x minus 3, x plus 2 is equal to 0. So now we have 2 more zeros. We have a +3 and a -2. All right, so now I need to find my y-intercept. So my y-intercept, again, is when x is 0. Well, that'll be 0, 0, 0. So again, it's just that constant term. So 0, 6 is my intercept. And then I want to talk about my end behavior. So as x approaches infinity, what does f of x do? Well, if we started on the right over here, right, if we're thinking about the wave, a is positive, so I would be starting above, so that means f of x is going to positive infinity. And then as x goes to negative infinity, what does f of x do? Well, it's odd, so it should be going in the opposite direction, so we should be going to negative infinity. So now we plot our points. So we have -1, -2, there's the 0. We have 1, and we have 3. And then our y-intercept is at 6. So we're going to go 1, 2, 3, 4, 5, 6. Okay, and again, we're starting above, so we start our line, we go through, we go up to that 0, and then we go back down. So there is our graphed polynomial. Okay, looking at number 8. Okay, so I see a negative and I see a coefficient. I know that before I look at anything here, I want to factor out that negative. When I have a negative in front of my leading coefficient, when I try to factor with it, it tends to just mess up my numbers and I don't get them quite right. So I'm going to factor out that negative, sorry, not the 2, just the negative. And then that's going to change all of my signs inside. So the negative became positive, the negative is going to become positive, and the positive is going to become negative. And now we want to think about, see if we can factor this. What multiplies to negative 12 and combines to positive 1? Well, that does factor. We could have a positive 4 and a negative 3. So we keep that negative out there. And then I have x plus 4 and x minus 3. Okay, now remember we are not done whenever we have a coefficient and we do our numbers. Because remember, each term needs to be divided by that leading coefficient. So it simplifies where it can, so that would be x plus 2. And then this doesn't reduce. And remember, because we're solving, we don't need to swing it because we just want the x alone. So now our zeros are negative 2 and positive 3/2. And again, you could have used rational root theorem here if you wanted to, but I could see that it factored, and so that's my preferred method. So then I'm going to talk about what's my y-intercept. Well, again, that's where x is 0, so 0, 0, just that constant 6. And now my end behavior. So as x goes to positive infinity, f of x approaches. Okay, so let's go back up and look. So we see it's a negative coefficient. So that means that instead of starting on the top right, we would be on the bottom right. And so then because it's even, it means our arrows will be pointing in the same direction. So as x goes to infinity, as it goes to the right, we're starting below because of that reflection. So f of x goes to negative infinity. And then again, because it is even, we know both of our arrows will be pointing in the same direction. So we come over here and we plot. So we've got -1, -2. There's my -2. Now 3/2, that's just 1 1/2. So I'm going to just put it in between my 1 and my 2. And then I do have that intercept at 6. So 1, 2, 3, 4, 5, 6. So we'll plot that. And again, because we are reflected, we're starting below, we go up, we hit our y-intercept and come back down. And again, it makes sense because it's even and it's a negative, so it should be a reflected parabola. All right, our last example. So again, I'm going to look and see, factoring is always my choice if I can do so. So I see that an x can come out here, so I'm going to take out that x, and I get x squared minus 6x plus 9. So then I think, okay, what multiplies to 9 and combines to -6? Well, that would be -3 and -3. So x times x minus 3, x minus 3. Now, we notice that we have that root twice. So that makes, we know we're going to have our 0, but that makes a 3, that double root. All right, and so now let's think about our y-intercept. Well, if I plug in 0 here for x, that's 0, that's 0, and that's 0. So our y-intercept here is just 0, 0. And now our end behavior. As x approaches infinity, f of x does what? Well, it's an even coefficient, so that means we're starting to the top right. So I'm going to be starting positive infinity. And then as x approaches negative infinity, I want to think about, is it odd or even? Should we be going the same way? Well, this one is odd. So if I am going to positive infinity on the right, then that means I'm going to negative infinity on the left. Okay, so I put my points in. I've got my 0, 0 for my y-intercept. And then I'm going to go over 1, 2, 3 to positive 3. And remember, 3 is a double root. So what happens at a double root? Remember, it bounces. So I'm going to be above the line. I bounce at that double root, and then I go back down through the 0. All right, and that is our last example for today. Please check in with your teacher if you have any questions or need additional tutoring. Thanks so much.